Hi everyone. Today I want to share an interesting topic with you guys. It's called network intrusion detection. First, let me restate this problem. Nowadays, there are many anomaly behaviors and malicious attacks on the network. For example, the denial of service attack, which is make some resource unavailable for some intended users. For example, although you have a very good network connection, you may cannot access to some Netflix or YouTube to watch some movies. It is really annoying. So, my task is to build a model or software to detect some known or even novel, unknown attack types. It sounds hard. Why? Because we need to predict too many attack types. In my dataset, I have already got 36 attack types. So I have two choices on dataset. The first is a reformulate NSLKDD dataset, and another is a standard benchmark KDD99 dataset. I choose a formal one. Why? First, the NSLKDD does not include redundant records, so my classifier will not be biased towards some more frequent records. Because it's very important. I don't want my classifier to oversize on some duplicate instance, which may capture some unimportant or irrelevant characteristics on sampling dataset. Another one is that the KDD99 dataset cannot really distinguish performance among the wide range of machine learning methods. It's hard for me to compare and do some error analysis among each machine learning method. And also, the NSLKDD dataset has a very good ratio between the train and test dataset. Before I introduce my model, I want to talk a little bit about data process. I will do two stuff. First, normalization. The second is nominal to numeric. The main reason I want to do that because I will do some distance calculation based on the feature vectors. So the first step, I need to transform some nominal to numeric values. And the second, I need to make my distance more meaningful, so I just project my original numeric value to the values between 0 and 1. And you can see here the normalization function. I project my numeric value into 0 and 1. Now, by the way, I implement all the R code in RStudio. R is a very good tool, good tools. And next is a baseline model. I used a random guess, and the performance is very low, of course, because I just randomly picked the class value from the 5 class value, normal, and the 4 main categories. I will mention these categories in following slides. I want to mention that I want to make a random guess as my baseline model. Is that I want to know how much my model learns, except some coincidence prediction. So my model is about the hierarchical classifier. There are basically 3 levels. The first level is nominal and abnormal. The second is 4 main categories: loss, R2R, U2R, and probing. And third is my prediction value. 12 training attack types plus 14 non-attack types only exist in the test dataset. So the reason I choose the hierarchical classifier is basically I want my model resolution higher, because you can see in my predict class value, I have a multi-class value, not 3, 4, 6, 5, 6, but 36. So in the traditional classifier, single classifier, the stronger or the more resolution my classifier has, my classifier will take more risk of overfitting in the unseen data. So, however, the classifier, hierarchical classifier, just to combine some not such strong classifiers into a tree structure, and this structure can overcome the overfitting on the test dataset. And we can see here is a clear tree structure of my whole models. Due to the space limit, I didn't list all the training data. Oh no, all the tag types. Okay, let's go to the details. First, I want to make sure the first part of my classifier has a very good performance, because it will greatly affect the following classifiers. So I choose a random forest. The random forest is just to grow some smaller trees, and each trees will have some predictions. And we want to use some ways like averaging, voting to combine these predictions. And this can reduce the variance from different varied from the different sampling data set. Such it's hard to overfit, and also it's very easy, can be easily implemented in the MapReduce paradigm. So why I choose MapReduce? Because for the first level of the whole model, the train data is relatively large. So we want to train the model multiple times for various reasons. For example, adjusting the parameters and do some error analysis. So it's really important for us to train the model efficiently. And MapReduce is a great parallel paradigm for us to speed our training. And also, after training, the model can be stored into the across the clusters, which make our future life more easier. Okay, here's the demo part. I want to show you how can I do some predictions using my pre-trained random forest models on Hadoop. So to save time, let me just first set up the environment, and let my MapReduce program run first. And then I will show some details. And I use the platform HortonWorks 2.2. It has a good interface of user interface to play with Hadoop on the virtual machine. And I also use Apache Mahout. It's a machine learning package in the Hadoop ecosystem. Here we can see the MapReduce task has started, and we let them run a little bit. And we can see in the HortonWorks I have several files. The OSL forest is a pre-trained model, and test data, train data, and the train.info is the data set. A file describes the attributes in my training set. And we can see, okay, the MapReduce job has done. And there are some, the results is as follows. And we have some summaries. and the confusion matrix, and more important, some statistics, kappa, accuracy. We can see that the speed is relatively fast, and the performance is not too bad, but it's not excellent. We need to prove, right? And after I refresh my web page, I can find that the prediction I got from the MapReduce job. I click it, and we can see the labels I predict for my each instance. Okay, let's move on to our next part, the second level. The second level, I use the decision tree cards, the classification and the regression trees. It's a little different from the ID3, which is the information gain split decision trees. It's very easy to interpret the results, and card has a property that in each node he will care about the misclassification rate. So he used this metric to help him to get the best split. Also, decision tree is very fast to train than weight-based classifier. For example, SVM. The reason SVM train very hard is first, there are many attributes, 41 attributes. SVM need to use all of them, but decision tree in each level, they may just a few features. Also, the training data set is pretty large. Here is a snapshot of my R code. And you can see I use the R package, R parts. And here is the clear visualization of my tree structure. In each node, you can see the conditions I used to get the splits. And these statistics is just the 4 categories, and the number of instances that fall into the different categories. And another worth notice that in each leaves, I don't have the U2R categories. I miss it. Why? After I inspecting the training dataset, I found that there are only 50 instances of U2R out of the whole training dataset. So it means that it is relatively very small to the whole training dataset, and we can just drop it for the sake of not overfit on the test dataset. So it's reasonable for card to just neglect the U2R categories. And in third level, I use a similar mind of the KNN. So let me go to in details, and you can see this graph is basically tells about the ideas. The black dots are just the data points with 41 attributes, and the color region is the attack types I want to predict. In each color regions, there are many data points, and the mean of these data points are just this white cross. And each white cross stands for a centroid, the centroid of the cluster. So when a new data point comes in, we just choose, or in other words, we just set the k of the k nearest neighbor equals to 1. So I just choose the 1 nearest neighbors. And we calculate, we use the Euclidean distance to measure this distance. And for example, if we get this central is the most closest one to my new data point, I just assign this color to this data point. Means the label. This is for how can I identify the known attack types. So for unknown or novel attack types, for example, here we may use some threshold to help us. For example, if this central is the most closest one, but it may be longer than the normal distance. So I may think that it's an unusual data types because its distance is so large than the normal distance. So I may consider this points as a new data type. So with each passing days, there are many data points come in, and we can use some unsupervised machine learning techniques such as the clustering, k-means, and then we can group some new clusters. And these are my new attack types. Now here is a snapshot of my code. This code just calculates the mean distance in each clusters of training data set between the data points and its clusters. And this is a distance. This is a distance, and this is a standard deviation of my distance. And this is a similarity. I use inclusion distance. Some statistics. The first columns means the attack types in the DOS category. I just list one category due to the space limit. And the second column is the distance between data points and my centroid. And the third column is the standard deviation between the distance and my mean distance. Here are some thoughts. This KN-like method is really good detecting known attack types, but is somewhat really weak on probing the new attack types. Why? As we know, a transformation from a transform from nominal values to numeric value may be problematic. Because first, the Euclidean distance may not a good similarity metric to measure the different attack types. Also, some nominal values assigned to some numeric values will not make much sense, since we don't have some domain knowledge to really characterize these nominal values using numeric values. So there'll be some unrealistic factors. But why I can get a good performance on detecting the known attack types? Let's make a comparison. And we can know that the naive Bayes, they use the naive conditional independence assumptions. So they may overemphasize some attributes, the importance. So each output may highly skewed. The result is overconfident. But it can also get a good performance in real applications because its relative comparison is hot. So although I get overconfident, but the relative comparison is right. So even his probability is untrustworthy but the decisions they make is probably right. So back to our KNN method, I compare distance between the other distance between each cluster's distance, or I choose the closest distance centrally. So the relative comparison may get a good performance, may predict the true labels. So that's why KNN method can work on detecting the known attack types. But as for the non-type, the evaluation is not good. As I mentioned, the Euclidean distance may not well characterize the difference among different attack types. And also, there's a famous sentence called the curse of dimensions. This is a very especially severe in the KNN method, KNN-like method, because as my dimension is has more dimensions, the dense data point distribution will be more sparse. So some intuition in the lower dimension will not hold in higher dimension, and we may need more data points to help us to do the k-nearest neighbors. But now, if we just have a higher dimension with a limited data points, each data point's distance may be changed, or interpretation may be changed. So, for example, if we just use KNN, we just have the 3 features, and we can be easily or precisely to choose the right parameter k and to get good performance. But now we have the 41 features. There are some irrelevant features to this category. So this will increase the dimension of my data points, and the data points, the distance will be smooth or be unrealistic to compare. This is a cursed dimension. And another is that the heuristics method may not work well because there's no guide to set a threshold. How far my distance with mean distance can be counted as the new data tag types? There's no guidance. So how about using train a classifier in each leaves of my second level descent trees? It could be more scientific than the KNN method, but it will increase my system complexity. So now, how to detect the null attack is still an open problem. Finally, let's put all together. Here I will walk through my code. First, I load the first level models, and I get some predictions, and calculate the accuracy. And then I do some data transformations to let my abnormal predictions into the next second level input. And I load the second level models. I do some prediction again, and calculate the accuracy of a second level. Then, in third levels, I write these assignment functions and do the predictions for each categories. There are the 4 main categories, and get the statistics. Okay. The final performance is about 73%, 0.61. It sounds pretty good. Remember, we have a 38. Oh, sorry. Maybe this is a typo. The 36 tag types. And the kappa, it's about 53.54, which means my model learned a pretty lot. So yeah, let's review my pipeline. We can have three of these models. And now if I want to further improve my whole system accuracy or kappa statistics, the first module I want to improve is just the first level, because it has lowest accuracy. So I want to do some feature engineering, but I come with some problems. First, I have no domain knowledge, because I'm not the network expert, so some features correlations I may not know well. And also just looking at the confusion matrix will take a little useful information. And my solution is feature selections. I want to use some machine learning techniques to help me to do some feature engineering. I use the weka tools, and there are some feature selection methods. For example, the information gain. It's just to calculate how the attributes is relevant to the class value. But it have some, it may not fit for my problem, because it just considers the single features correlation with the predict class, but it neglects the combined features power with my class value. So I choose the subset evaluation. Is just choose the subset features that are highly related with the classes, while have a lower intercorrelations. So I may avoid some circumstance in information gain that I have the good features that have related strongly with my class value, but they are correlated, so it may affect my classifier performance. The method I use the best first is a greedy algorithm, and I shrink the 42 features to 6 features. The performance is get a little higher, about 79 and 49.34%. Oh, by the way, this is a performance in my first level. Summary. The intrusion detection system is not easy to build because there are many attack types we want to predict. And we also to deal with every day may appear some novel attack. Hierarchical classifier and feature selection is a very powerful in this method, because the model we can to choose the best group of features and use these features to build a strong or high resolutions models. Our MapReduce and Weka are really good tools for their scientists to do some big data analysis, and it's very easy to manipulate some data statistics, and MapReduce is very good for train the model fast. Of course, we have a lot of future work to do. Novel detection is still a very hard problem, and we should cooperate or incorporate some domain knowledge into our visual engineering. So we need to cooperate with some students in these majors, or get some help from experts in this domain. So thank you. This is my brief introduction in the novel network intrusion big data practice. Thank you.